Is it echoing now? Uh, Sorry for that. Can you just write now whether it is okay? Okay. Thank you. Yeah, so I hope most of you might have gone through the weekly contents. So this session was the this week content was mainly on governing equations involved in CFD, and along with that the PDE classification, the classification of partial differential equation. Okay, so let me briefly recap what you have studied in week one. So first part was introduction to CFD, wherein you learned what is computational fluid dynamics and mainly what are the application domains in CFD. Also, you also learned why you need to study CFD, what is the competitive advantage of CFD over other procedures, and also the various steps which are involved in CFD study. Now, let me ask one particular question. So, can you please write down in the chat box what are the main application areas of computational fluid dynamics? You can write in the chat box. Okay, aerodynamic analysis, flight simulation, flow simulation, heat transfer. Yeah, that is mainly related to the physics which you are writing. I mean, to simulate what kind of physics we are using computational fluid dynamics. That is absolutely right. Yeah, so now I am getting some answers like automobile energy studies, aerodynamics, weather analysis. Yeah, so if you see the applications, they are almost in every sector. Say from weather analysis, which one of you have written, to even blood flow, which recently I have got in chat box. Okay, blood flow, cardiovascular, yeah. So these are like recent trends, especially in the biomedical sector. You see, computational fluid dynamics is being aggressively used. Okay, yeah, in nanofluids also, and mainly in micro channel flows you kind of use computational fluid dynamics, and you use computational fluid dynamics mainly to come up with a new device which can give maybe better performance over the previous one, or else you also need to use CFD, especially in biomedical sector, wherein you just cannot perform experiments. Now, if I give a one particular example of this, assume that a stent needs to be inserted in a patient's artery. So his artery has got blocked, and usually surgeons operate the blocked artery by inserting stents, okay, which kind of unblock the artery. So now, to understand which geometry of stent will suit best for that patient, you cannot do trial and error on the patient, okay, so that is just not possible. So in that situation, you can extract the geometry of the patient and then maybe perform a computational fluid dynamics analysis to see which design suits best, okay. So in such situation, CFD is the only option. If you see some other fields like aerodynamics and all, okay, so there at least you have some wind tunnel tests and all which you can perform. So but again, CFD is not very expensive and it's not very time consuming, okay. So in that way it offers advantage. So The advantages of CFD are mainly in many fields. You take the name and you get the advantage of CFD. You get an application area of CFD. Okay, so that is the main appreciation which you should have before learning this subject. So once you kind of understand the areas wherein this can be applied, then you get more interested into the course. So that is why I was highlighting mainly on this particular point only. Okay, and also can someone write what are the brief steps which you kind of perform in CFD, like starting from the identification of the problem, what are the next steps followed? Can somebody write down? Yeah, modeling, meshing, and simulation, creating geometry, selecting suitable equations. Yes, so all of these are correct answers. But if we see in a step by step manner, so the first step is to identify the problem and the physics which suits that problem. So if you want to say analyze just the heat distribution in a solid wall, so there you need not do any flow analysis. You only need to solve uh, energy equation in that particular situation. So you need to analyze the physics. And if you have say air and water interface like waves splashing on the surface of some stone and all, if you have some such situation, you have to go for multi-phase modeling wherein you have air also and water also. Okay, so that is again a different physics. So you have to identify the physics first, define the governing equations for that particular physics. So that is the first thing. Okay, so once you do that, then you kind of can identify the domain and create the geometry of your problem. Okay, and then discretize it into small number of elements which you call it as meshing. Okay, and then put the suitable boundary conditions for the domain and identify the flow parameters, and then you can do the simulation. Okay, so this is nothing but application. Okay, now the last part is analysis. So for example, if you are doing flow analysis over an aircraft, okay, so the main parameter of interest for you would be lift and drag forces mainly. You have to calculate that from the pressure and flow velocities which you are getting. Okay, so that is the post processing. Okay, so these are basically the steps which you have to follow in a systematic way so as to come up with a correct accurate answers, I would say. Okay, so that was the first part. In the second part, you studied governing equations. Okay, so governing equations, first you started with the basic Laplace equation. Okay, um, and then unsteady state heat conduction equation. uh, can anyone tell me what is the main uh, order of Laplace equation? You can write in the chat box. Yeah, it is second order because you had um, d square t by dx square plus d square t or phi, whatever it is the value of the variable, phi divided by dy square. Okay, so it's the second order. We will look into it in the sample problems also today. Okay, and then you had incompressible Navier Stokes equations. Okay, so mainly when the density of the fluid is varying with respect to the pressure and temperature, so in those cases the fluid becomes incompressible in nature. Sorry, compressible in nature, and you solve compressible Navier Stokes equation. And if at all there is no variation in the density, then you come up with incompressible Navier Stokes equation. Okay, And lastly, you saw the classification of partial differential equations. Now, whenever you kind of get any physics which you want to solve, you have to come up with the governing equations for that, and then you have to classify the PDs. Now, let me ask you one question. Why do you need to classify it? Why do you need to classify partial differential equations? Uh, can any one of you write down in the chat box why we have to classify the partial differential equations? What is the necessity to know if it is elliptic, parabolic? Okay, so that is correct. But again, why you have to know it is whether it is okay to understand the nature of solution. Yeah, and different methods to solve. Yeah, to know common value. Okay, so yeah, you have to know whether it is elliptic, parabolic, or hyperbolic. But the main thing is, you have to understand, as written by some of you, to understand the nature of solution. Yes, and mainly to understand which method will suit that particular equation. To solve that particular equation, which method will suit. Okay, so that is the main agenda behind classifying the partial differential equations. Once you kind of classify them, you will understand what will be the nature of solutions. Yes, but along with that, you will also understand which methods you have to use, because that is very important to obtain accurate solution and consistent solution. Otherwise, you will land up with some diverging solutions or something like that. Okay, so that is the main agenda. Okay, so this was a brief recap of whatever you studied in week one. Okay, I hope this is pretty much clear. If you have any doubts, we will open the session at the end. You can maybe ask me in the chat box. Okay. So let us just briefly revise about the partial differential equations, because mainly your questions are mainly from this partial differential equations itself. Okay, so mainly you have order of partial differential equation. So order of partial differential equation is mainly determined by the highest derivative in the equation. Now, what is meant by highest derivative? So, if you have, for example, dou phi by dou x, okay, so that is just a first derivative. Now, you can have dou phi by dou by dou x of again dou phi by dou x. Okay, so there you are differentiating the variable two times, dou by dou x again dou phi by dou x. Okay, so mainly then it becomes a second order partial differential equation. So in that way you define the order. So order is mainly determined by highest derivative which is there. It can have first order also, second order also, third order also, but usually the order, the meaning of order is the highest one which is there. Okay, so you can see the examples also, I hope, in this particular picture. Okay, and then you have linear and non-linear partial differential equations. So whenever in a partial differential equations, if the differential is of first degree, now degree means the power to which the derivative is raised. So here it is raised to the power 2 in this particular equation. So the power needs to be of 1, okay, for the derivative as well as the variable. Then only the PDE will become linear, otherwise it will be non-linear. Okay, so as given here, so you can see u square is there, so that is why it has become non-linear. Here it is dou u by dou x2 whole square, so that is why it is non-linear. So both have to be of first degree. Okay, in that case it will become linear partial differential equation. Okay, so you need to understand these things to again to come up with a good strategy to solve the problems. Okay, which time stepping you have to use, okay, which discretization you have to use. So classification is used to mainly understand this. Okay. So the last thing which you studied was homogeneous and non-homogeneous partial differential equations. Now, if you kind of consider all the derivative terms on the left hand side, and if you club them together as say L of u, where L indicates this linear operator and it mainly consists of this derivative terms. Now on the right hand side you get a term. If you have a term which is non-zero, okay, then it becomes a non-homogeneous equation. So basically you have the right hand term only in terms of independent variables. Okay, if it is u1 plus u2, then whether it will become homogeneous or non-homogeneous, can you write in the chat box? So u1 and u2 are not there, say only u is there, is equal to u in this particular second equation. Is it echoing now? Somebody has written it is echoing. Is my voice echoing? Uh, no, right? Okay, okay, fine. I hope that my voice is not echoing. Okay. Can others also write down whether my voice is echoing or not? Okay, okay, yeah. Many of you have written that it's not echoing. Okay, yeah. So mainly this function, as it is written here, it should be in terms of x1, x2, x3, t. Only then it will become okay non-homogeneous. If you have u, okay, it is a dependent variable, it will be still homogeneous only. Okay, in that case, yeah. So some of you have written that it is homogeneous. Okay, now the last thing is classification. As you already have written down that we need to understand the nature of solution and which method we have to use to classify the PDE. That is the main intention behind classifying the PDE. So if you kind of organize your partial differential equations uh, in this particular form, wherein you have second derivative of with respect to one independent variable and second derivative with respect to other independent variable x2 in this particular form, so mainly you can understand the nature of equation by getting to know the roots of this particular equation. So if the term b square minus 4ac, if the root that becomes positive, then you kind of classify it as say elliptic or the parabolic when it is equal to 0, and if it is greater than 0, then say you would call it as hyperbolic because there are real roots. So there is a discontinuity which kind of propagates with respect to time, and that is why the equation kind of becomes hyperbolic in nature when you have b square minus 4ac equal to sorry, it's greater than 0. So let us come to the first tutorial problems. Okay, so I'll try to wrap it up within half an hour, and if you have any doubts you can ask in between also. So what is the order of the following differential equation? So I think it is very easy question. Can you write down in the chat box what should be the answer for this question? Yeah, many of you have already written it down. So it is a second order. So if we expand this equation like as shown in this particular uh, figure here, so you can expand it as dou by dou x of again dou u by dou x, right? So in that way you have two differential terms, that is why the order becomes second order. Okay, So let us go to the next question. Again, it is the same set of question. What is the order of the following partial differential equation? Okay, so can you write the answer for this? Yeah, again it is 2. One more question which I'll ask. What is the degree of this equation? Can you write down degree of the equation? Yeah, so the degree should be equal to 3 here, because this second partial derivative has been raised to power of 3, that is the exponent, highest exponent. Okay. Also one more thing. Hmm, can you answer whether this equation is linear or not? Okay, so many of you have written non-linear, because the definition of linear itself tells that the degree should be 1 of the partial derivative. So degree itself is here 3, so that is why it is non-linear. Okay, so we had discussed this just a while ago. Okay, so you call a partial differential equation to be linear when its degree is 1, and for the partial derivative as well as for the variable. So if you had u, then also it would become linear plus u. If you had plus u square on the right hand side, say, then it would become again non-linear. Okay, so as of now it is non-linear because the exponent here it is 3. Okay, so yeah, so the correct answer here is that it is a second order equation. So this is a problem wherein you have to work out. Okay, um, the given equation does not satisfy Laplace equation. State true or false. So how do you say whether it is satisfying Laplace equation or not? Can you write down in the chat box? So basically, v is equal to tan inverse y by x is there. So we need to understand whether this satisfies Laplace equation or not. Can you write in the chat box, uh, how do you determine whether this equation satisfies Laplace equation or not? No, no, I don't want the answer. You are writing the answer already, I think. True, true, you are writing. Okay. Uh, how do you get to know that? Okay. Del square phi by del x square. Okay. Yeah. Del square phi by del x square you have written. Okay. So del x square plus this is also a term which is dependent on y also, so del square v by del y square also you have to calculate. Okay, so try to read the question properly. The question says the given equation does not satisfy Laplace equation. So let us see one thing. Let us check whether it satisfies Laplace equation or not first, then we can maybe answer. So in order to check that, you can maybe take del square v, that is del square v by del x square plus del square v by del y square. So if you try to work it out, okay, del v by del x, it should come to 2xy divided by x square plus y square whole square. So you can try to work this out, okay, and tell me what should be the value of del square v by del y square. Okay, you can write in the chat box. what should be the value of del square V by del Y square, because that is the thing which is remaining. I would suggest that for this session, you should sit with a pen and paper, okay? Whenever I try to solve these problems, you should be also solving them with me. Only then you will get a practice and you will understand the subject in a better way. Yeah, maybe I will share this PPT, okay? This PPT will be shared with you anyways, okay? But I want you to solve on paper del square V by del Y square and let me know the answer. Yeah, some of you have written minus 2xy divided by x square plus y square the whole square, okay? So I think you might land up with this particular equation, that del square p by del y square is equal to minus 2xy divided by x square plus y square the whole square, okay, which is exactly of the same magnitude but of the opposite sign of del square v by del x square, okay. Yeah, good. So many of you have got the correct answer, okay. So what will happen if we add up? It will definitely turn out to be 0. Okay. So what should be the answer then? You can write down in the chat box. Yeah, it should be false. So you should try to read the question properly. Okay. The question is reading the given equation does not satisfy Laplace equation, but it is satisfying Laplace equation. So the answer is false because some of you had written true in the initial stages, I think. Okay. So okay, so false is the correct answer. Okay, now the fourth question is as follows. So Laplace equation is a statement number one says a second order partial differential equation, whereas statement two says a homogeneous partial differential equation. We just now saw what is Laplace equation. Okay, so based on that, can you give the correct answer? Okay. C. Both are true. Both the statements are true. Exactly. Because it is del square phi by del x square plus del square phi by del y square. Now, I would ask one more question. Can you write down whether it is linear or non-linear? Linear. Okay. Okay. Yeah. It's a linear equation because we have the degree of all the partial derivatives as one only, and there are no separate variables which are there in this particular equation. Okay. Yeah. So the order is 2 and the homogeneity is correct, that it is homogeneous because f is equal to 0 here, okay, that is why it is 0. Now I would ask you one question at this particular point. Now assume that you have a unsteady state heat conduction with some volumetric heat generation, okay, uh, which kind of depends on the uh, domain length, okay. So in that case, what would be the correct answer? You have an unsteady state heat conduction okay, and then you also have some volumetric heat generation. uh, it depends on the length of the domain or the position in the domain, okay. In that case, what would be the correct option amongst A, B, C, D? Yes, it would be linear, but whether it would be homogeneous in that particular case? No, it wouldn't be homogeneous, right? It would be non-homogeneous because you have a term f, okay, which is dependent on the independent variable, that is the coordinate, okay. So there is a term which is dependent on the coordinate, that is the volumetric heat generation term, okay, which comes on the right hand side. So that is why it would become non-homogeneous, and that is why which statement would be correct. Statement 1 is true, statement 2 is false, so A would be the correct option. Yeah, many of you have indicated that. Very good. So let us move on to the next question. Yeah, again it's the same thing. What is the order of the governing equation of unsteady state heat equation? Okay, so you have already indicated it in the last question only. So it is quite simple, I think. Yeah. So you have the transient term, which is the rho Cp uh, and derivative of temperature with respect to time, which is equal to the K into del square T. That is the thermal conductivity K, and Cp is the heat capacity of the material. Okay. So this particular equation is a second order equation. So yeah, so sixth question it is as follows. So Euler equations are a system of dash, okay, which comprise of system of again dash, okay. So can you write down the answer in the chat box for this particular question? First of all, uh, before writing the answer, what are Euler equations according to you? What do they describe? What is the physics which they describe? Can you write down in the chat box? What is the physics which these Euler equations describe? So let me give a hint, okay? So they are conservation laws, definitely yes. Conservation laws for what? Inviscid, ideal flow, momentum, conservation. Yeah, they are conservation law, and they are applicable for inviscid flow, okay? But can you tell me whether it is a conservation law for compressible or incompressible? What is the mass conservation which you have in Euler equations? The first term is dou rho by dou t. Okay, so density is varying with respect to temperature here. Yeah, you can say it to be both because you can ignore the term, okay, of this particular dou rho by dou t, but it is mainly intended for compressible flows, not incompressible. Yeah, you can extend it, like just an approximation would become incompressible, but mainly you have rho by dou t also, which is included in the Euler equation. Okay, so in that sense it can be applied to compressible flows also. Okay, in viscid, yeah, that is true. Okay, so is there any query on this? Because many people I saw had written only incompressible as the option. So is this clear what I told just now? Can you write in the chat box? It is for inviscid, but you can use it for compressible also. Okay, so some of you are telling me to repeat it. Okay, so if you just consider a 1D Euler equations, so the equations are of this form. Okay, dou u by dou t plus dou f by dou x equal to 0. Say this u is a matrix, okay, which comprises of these particular terms here. So basically they are conservation equations which consists of mass conservation and momentum conservation, and third is the energy conservation here. Okay, I have considered just a 1D domain. Okay, so in the first equation you have kind of dou rho by dou t also coming into the picture. Okay, so and then you have as usual dou by dou x of rho u, which is equal to 0. So it can be applied to compressible flows also, inviscid in nature. In incompressible flows you have only dou by dou x of rho u is equal to 0. You don't have dou rho by dou t term, okay, in incompressible flows. Okay, so what I am telling is that this Euler equations can be mainly applied to compressible. As an extension, definitely it can be applied for incompressible also, but mainly it is for compressible. Is this clear now? Okay, maybe you can go through this again. Okay, this content mainly on Euler equation. Okay, because this is mainly useful, I think, for people from um, aerospace background. Okay, first of all, sorry for that, I did not introduce myself to all of you. Okay, so sorry, I just forgot that. I am Sumant Morab. Okay, I am a PhD research scholar in Department of Mechanical Engineering in IIT Bombay. Okay, so as a part of this NPTEL course, I'll be conducting the tutorial session every week. Okay, on every Friday from 7 to 8 I'll be conducting this tutorial session wherein we will be seeing some of the sample problems of the weekly content. Okay, and then if you have any queries you can just ask like this in between the questions, and regarding the weekly content you can ask at the end. Okay, so sorry for that, I did not give an introduction of myself. Okay, so I am mainly from a mechanical background, so these equations mainly find their application in aerospace field. Okay, now again there is a question on compressible Navier-Stokes equation. Okay, so the question is as compared to the number of unknowns, what is the number of equations which you have? So there are dash number of unknowns compared to the number of conservation equations. So can you write the answer for this? You know, there are less number of unknowns compared to conservation equations. Okay, there are more. So okay, let us do this step by step. What are the unknowns? Can you write in the chat box? What are the unknowns in a compressible Navier-Stokes equation? What are the variables which are unknown? Before jumping into the answer, let us do step by step analysis. What are the unknowns? Can you write in the chat box? Unknown variables, yeah. Unknown variables, yeah. Density, velocity in x, y, z direction, pressure, u, v, w. Some people are including pressure, some people are including density. Okay. Uh, psi, density, pressure. It is psi, pressure, forces. Okay, I want the total number of unknowns. Like, what are the unknowns? Complete set. So in a way, you are right in telling density, velocity, and then some of you have written pressure, UVW, okay. And then one of you have written pressure forces, body forces, surface forces. That comes in the conservation equation. Okay. I wanted to know the unknown variables. So yeah, since you are dealing with compressible Navier-Stokes equation, you have density as an unknown. Anyway, velocity is unknown, velocity in xyz direction. You have also pressure unknown, okay, right? And you have also energy term which is unknown, okay, the thermal energy you can say. So how many unknowns are there then? You have density, uh, velocity, and you have pressure, okay. Pressure, if you say it comes in terms of energy, but temperature is again an unknown. So you totally have 6 unknowns which can be seen in this slide. But equations, you already know that you have only 5 equations. For mass, 1 equation you have, momentum 3 equations you have, momentum conservation, and for energy conservation you have 1 equation. So totally you have 5 equations. But whereas you have 6 unknowns. Okay. So in a sense, if you see only Navier-Stokes equation, then definitely there are more number of unknowns than the number of conservation equations. Okay, this is just a partial picture. Okay, this is little bit tricky question. Okay, because they have mainly asked for Navier-Stokes equation, but whereas if you see this cannot be a physical reality, then you can never get a solution if this is the case. So you have something called as closure equations, which is the equation of state, wherein you kind of relate pressure and temperature, okay, through the energy equation. Okay, so mainly you have P is equal to rho c square in terms of, say, for acoustic terms if you want to solve, or you have a relation between the temperature and pressure using the ratio of specific heat. Okay, that is which comes in equation of state. It's not a Navier-Stokes equation. So that particular sixth equation is used to close the gap. Okay, so after that, what will happen is the number of unknowns will be equal to the number of conservation equations. Okay, so if you see, the answer should be more because they have asked only Navier-Stokes equation. If they have asked all the conservation equations, then it should be D, greater than or equal to, okay, because we close the equations using the equation of state. Okay, so in this particular context, it should be A, the option A, which is more. That is, if you see only Navier-Stokes equation, then there are more number of unknowns as compared to the number of conservation equations. I hope this is clear. Okay. So some of you had written D. Okay, D is also in a way correct, but not for this particular question. Okay, so if you add a equation of state, yeah, then what happens is the number of unknowns are equal to the number of conservation equations. Okay, so I hope this is clear. So let us move to probably the last question. Yeah, because we are running out of time also. Okay, so the study two-dimensional velocity potential equation is given by this particular equation, which involves Mach number on partial derivative of a variable. Now the question asked is, what is the nature of the given equation for supersonic flows, which means m is greater than 1, which means 1 minus m square is less than 0, that is, it is negative. Okay, because m is greater than 1. Okay, so 1 minus m square will be negative. So in that case, uh, how do you determine the nature of the equation? Can you write down that in chat box before going into the final answer? Okay, b square minus 4ac. Okay, you, these p square minus 4acs are nothing but uh, part of the root equations, which kind of tells us the direction of propagation of the solution. Okay, that you might have learned in the theory. Okay, so in that particular equation, while finding the root, you get a term known as square root of b square minus 4ac. So depending on the nature of this p square minus 4ac only, you can determine the nature. Okay, so what is a and b? Can you write down in the chat box here? Now we have to find b square minus 4ac, but what is a and what is b in this particular equation? A is equal to 1 minus m square, b is equal to 0. Yeah, c, sorry, I forgot c. C is equal to 1. Okay, so if we compare it with this particular standard format, which I had shown it in the second slide also, then you kind of come up with this: a is equal to 1 minus m square, which is less than 0, b is equal to 0, c is equal to 1. And if you find b square minus 4ac, it becomes minus 4 into 1 minus m square. Okay, since 1 minus m square is already less than 0, so this whole term becomes positive. B square minus 4ac becomes positive. Okay, so since b square minus 4ac is positive, okay, maybe this has been indicated incorrectly here. Okay, it should be hyperbolic. A is correct answer. Okay, uh, this is a mistake here, it should not be c, it should be a, hyperbolic equation. Okay, so yeah, so okay, let us wrap it up here itself. If you have any queries regarding any of the content, weekly content, maybe you can write down in the chat box. Okay, and one more thing is, this is the first session which I have conducted, and it was just based on the introduction to your governing equations and then the classification of partial differential equations. Later on we will move with some complex examples also in the later weeks as time proceeds. Okay, so every week from 7 to 8 we will be having this particular session. Okay, so I wanted to know a general feedback regarding my voice quality, and also regarding the presentation, whether it was readable or not for you guys. Just can you write some comments? Okay, so many of you have written a question: how do you find the eigenvalues of a PDE? Okay, so mainly this question was based on that only. Okay, uh, basically you have to calculate this particular matrix A here. Okay, so I have taken a very simple case here. Okay, wherein you formulate the A matrix. Okay, so it should be in the format A phi xx plus B phi xy plus again another term B, which is phi yx. Okay, which is nothing but phi xy. That is why I have split it into b by 2, b by 2 here, and then c. Okay, so this forms our A matrix. And if you kind of use this formulation, A minus lambda I determinant equal to 0, then you can then find out this eigenvalue. Okay, so that is the particular method in which you find the eigenvalue. Be sure to split this up, okay, because in the standard format it is actually b1 phi xy plus b2 phi yx. I have just split it up into two parts here, b by 2, b by 2. Okay, is this clear how to find the eigenvalues? In this question it was given that already an eigenvalue is 0, then we have to find something else, but generally that is the method. Okay, many of you have said that it was good. Some of you have also written that the voice sometimes was breaking. Okay, okay. Next time I will try to ensure that that will not happen, and I will try to see this recording itself and where it was breaking, and I'll try to analyze why it was breaking. Okay, okay, that's fine. Uh, did you get the answer for this question? How to find the eigenvalue of a PDE? Some of you had asked this question repeatedly. That is why I. Okay, okay, fine. Yes, sir. Okay, thank you. Okay, so one of you have also asked me, what is your topic in PhD? Okay, so I am from mechanical department in IIT Bombay, and currently I work on development of numerical methods for solving fluid structure acoustic equations. Okay, we mainly solve multiphysics equations. So we mainly develop computer programs to solve these equations. So in this particular course you will be developing equations to solve the fluid flow equations. So similarly, I develop multi-physics solvers. Okay, that is the first part, and then after developing that, mainly I use that solver to I apply it in biomedical field. Okay, so there are some biomedical problems which we try to solve, mainly on the blocked arteries, as I was speaking just in the introduction section. So we try to use the solver which we have developed to get out any useful information for clinical surgeons. So in what conditions the design might be better, or in what conditions the surgery might be necessary. So to give a predictive statements regarding that, we use our solvers. Okay, so it's not the stent problem, it's a bit different actually. So based on the flow physics, we try to detect what is the sound which might be heard by a stethoscope, which is usually used by a doctor. And based on the sound signal, what is the constriction level in the artery, and how urgent it is required, a surgery is required. Okay, so that we will be try to predict. Okay. Okay, so many of you have asked books also. Okay, mainly you can find uh, uh, the books, I think, in the content of this NPTEL course. But I personally followed uh, numerical heat transfer and fluid flow book, that is was by Patankar, and then introduction to CFD, I think finite volume methodology by Malala Sekara. Okay, so Malasekhan, sorry. So that was the book which I personally followed. I don't know whether it will be very much in sync with what you learn in this course or not. Yeah, but general CFD, I have followed those books. Okay, so I hope those will be very good, especially if you are trying to build a computer program with a solver with a finite volume methodology. Okay, so those books will be good. Apart from that, you can also follow what is there in your. Okay. How to understand easily this course? Okay, so I would say that just follow the contents which are being taught in this course on a weekly basis, and also try to attend the tutorial session, okay, which will help you to get a practice to solve your assignment problems also. So when you do practice multiple times, okay, then you become quite comfortable with the contents of the course, okay, and do it on a regular basis, like every week you have to be solving this problem, so that whenever you go to the next topic you will understand it very easily, because you don't have a lag in between, okay. So usually that is the way in which any course goes on, okay. So whenever you kind of get some practice over the questions, that is when you really learn the subject, okay. So for this tutorial session also I will suggest you that you sit with a pen and paper, okay. Okay, you have to be solving along with me, since today it was very small questions, we were just going through it. Next time what I will do is I'll give 5 minutes time, so that you guys can solve, and then maybe I'll discuss the answer, okay. So no, no, you cannot edit the source code in ANSYS. That is what I think. I do not have much experience with the ANSYS anyways. But as far as I know, I don't think you can edit the source code. You can edit the source code only in OpenFOAM software. Okay. So OpenFOAM is an open source software. Okay, there you get solvers and their codes also. So you can just modify those codes for your problem of interest, and then maybe you use it, okay. But in ANSYS I don't think you can do that. OpenFOAM, yeah, definitely is the best option, because you kind of get a software like feel also, and then you can do development also. If you want to solve some new equations, then you can couple it with already existing flow solver very easily. So yeah, OpenFOAM is a very good software which you can learn, okay. I would not call it as a software anyway, okay. Any other queries? Okay, so this class will be every week, Friday, uh, 7 to 8 p.m. Okay, you can join through this Google Meet link. These PPT will be shared with you. Okay. Okay, I think these were the questions. Yeah. Thank you for attending the class. Okay. I hope to see you in the next class also. Also on Sunday also you will be having a tutorial session by another TA. Okay. So you can feel free to join that also. Okay. Okay. Thank you.